Hello, welcome to the course Excelling with Mathematical Modeling. Today we will be talking about forensic model. For that, we need to know this law, Newton's law of cooling. So, the whole theory is based on this law. So, what does that law tells? It says the rate of change of the temperature of an object is proportional to the difference between its own temperature and the ambient temperature. So, by ambient temperature we mean temperature of its surroundings. So, if you want to mathematically write this, so the rate of change of temperature is proportional to the difference. So, the rate of change in discrete case is given by this, that is the temperature after n generation or after n time and the difference between the n plus 1th time. So, this is the rate of change and it is proportional to the difference between its own temperature, that is your Tn, and the ambient temperature, that is its surroundings, which we can take as some S. So, it is some S minus Tn and this is proportional to this. So, you can write Tn plus 1 minus Tn, some constant of proportionality S minus Tn. Now, one can ask that, okay, if I write Tn minus S, what will happen? Well, nothing will happen, it is proportional to the difference. So, whether you write this one first or this one first really does not matter, because it will be taken care by this constant of proportionality. If for one case it comes positive, for the other case it will come negative. So, it will be adjusted. So, you do not have to worry about this, you can take any one of them as the first and the second one as the second. So, here your Tn is the temperature of the object after some time, say some n minutes, can be n hours also. S is the surrounding temperature and K is the constant of proportionality. Now, suppose you have a cup of coffee in the room. Say the temperature is 190 degree Fahrenheit, and say after 1 minute it becomes 180 degree Fahrenheit after 1 minute. So, your equation was Tn plus 1 minus Tn is equal to some K times S minus Tn. So, in this particular case, the S is the surrounding temperature or the room temperature, which we take as 70 degree Fahrenheit. Now, I put say n equal to 0. So, you get T1 minus T0 is equal to some K S minus T0. So, your T1 was 180, your T0 initially at 90, K you do not know, this is your 70 and your T0 is 190. So, you get this particular equation, you can just solve it. So, minus 10 is equal to k times minus 120. So, k is 10 by 120 equal to 1 by 12. So, you can substitute it here, Tn minus 1 minus Tn is equal to 1 by 12, it is 70 minus Tn. If I multiply Tn plus 1 equal to Tn minus Tn by 12 plus 70 by 12. So, Tn plus 1 equal to 11 by 12 Tn plus 70 by 12. So, this equation Tn plus 1 is equal to 11 by 12 Tn plus 70 by 12. It has the form un plus 1 equal to aun plus b. You can either recall the solution or, but it is quite easy to derive. So, if I write un plus 1 equal to aun plus b, then un is a times un minus 1 plus b, un minus 1 is a times un minus 2 plus b, and so on. So, we use that, you substitute this un here. So, a times un minus 1 plus b equal to a square un minus 1 plus ab plus b, and this you can write a square un minus 1 plus b into a plus 1. Similarly, this is substituted here and you get a square aun minus 2 plus b into a plus 1. This is a cube un minus 2 plus a square b plus b into a plus 1, and a cube un minus 2 plus b taken common a square plus a plus 1. If you generalize this, un plus 1 is equal to, so this is 3, this is 1 less, this is 1 less. So, if I replace this by a to the power n, then this becomes, or rather if I put this as, if I want to make this 0, then this will be a to the power n plus 1 u0 plus b times, this is a to the power 1 less. So, n plus a n minus 1 plus a plus 1. So, you generalize it like this, that if this has to be 0 and then this becomes 3, then this is 2. So, 1 less. So, if I put this as n plus 1, this will be u0 and this will be n, 1 less than this. So, if I now compare it with this particular equation, I will get Tn plus 1. So, this is the a and this is the b, which is 11 by 12 to the power n plus 1 into T0 plus b is 70 by 12, and this is 1 minus a to the power n plus 1 by 1 minus a, because your a is equal to 11 by 12, which is less than 1. So, I can write Tn plus 1 is equal to 11 by 12 to the power n plus 1 into T0 plus b, which is 70 by 12, 1 minus a to the power n plus 1 by 1 minus a, where your a is equal to 11 by 12 and is less than 1. So, this 11 by 12 to the power n plus 1 into T0 was 190 degree Fahrenheit plus 70 by 12 1 minus 11 by 12 to the power n plus 1 minus 11 by 12. So, if you simplify this, this is 11 by 12 to the power n plus 1 into 190 plus this is 1 by 12. So, 70 minus 70 times 11 by 12 to the power n plus 1. So, this will be 70 plus 120 times 11 by 12 to the power n plus 1. So, this is the equation which you get for a cup of coffee which was kept at the surrounding temperature, which is the room temperature at 70 degree Fahrenheit. So, what happens in the long run? So, as your n becomes large, you see that your Tn plus 1, it approaches the room temperature, because 11 by 12 is less than 1. So, this particular thing tends to zero. We now look into the numerical solution. The equation which we will be solving is Tn plus 1 equal to 11 by 12 Tn plus 70 by 12. If I want to change the font size, make it 20, so I just and I make it bold. So, this is the equation which shows a cup of coffee is kept in a room, and we want to see in the long run at what temperature the coffee becomes. If you want to type this in equation, so you have to go to this insert and you have to click this equation, and you will see such a thing will appear. So, if I want Tn plus 1, I will go here and I will click this one for the subscript. So, this is your T and this will be your n plus 1, and that is equal to Tn. Here it is Tn. If you need a fraction, you have to go here fraction and click this. This will give 11 divided by 12 plus another fraction which is 70 divided by 12. So, basically this equation written in mathematical form. If you want to increase the font size, I can make it 20 and bold, and I can put it here. So, the same equation in the mathematical form by going to insert and this clicking this equation. Let us now solve this difference equation. So, we put n here, Tn here at time 0, this value is 190 degree Fahrenheit. I just increase the font to 20 and middle the values. So, this is equal to this plus 1. Say let us calculate this one. This is equal to 11 by 12. So, 11 divided by 12. I put it in a bracket, and this is multiplied by T0 190 plus 70 divided by 12. I also put this one in a bracket and end. So let me now drag this a little more. So as you can see, say up to 100 values. So as your time becomes large, the cup of coffee reaches the value 70 Fahrenheit, which was the room temperature. So we now plot this graph and we will get a clear picture here. So I highlight them, I go to insert, click the chart and thus. So I remove the grid lines, I put axis title, x-axis is the time and y-axis is the temperature, and temperature of a cup of coffee. So as you can see that with time this approaches the steady state 70 Fahrenheit, which matches with our analytical result. So this is what the application of Newton's law of cooling. Now let us see how this law can be applied to a forensic model. So what does this forensics do? Generally when there is murder or any sort of crime, this team goes there and try to collect evidences. So this particular law will be used to calculate the approximate time of murder and how it is done. So let us formulate the problem. So suppose a group of investigators, they got a call, or the police get a call that there has been a murder in the neighborhood, and say at 5 a.m. the team of investigators arrive. So they took the temperature of the body, and they find that it is 87.5 degree Fahrenheit. So then the body is removed, and after 1 hour, when the body is to be shifted to somewhere, so after 1 hour they again took the temperature and it is 80.4 degree Fahrenheit. So the normal body temperature of a live person can be approximately taken as 98.6 degree Fahrenheit. So now the question is, find the time when the victim was murdered. So We will be using this Newton's law of cooling to find an approximate time when the victim was murdered, and this is exactly what is done in the real life scenario also. So, once again the gist of the problem is that there has been a murder in the neighborhood, the police got a call and the first team of investigator arrives at 5 a.m. They took the temperature of the body, which was 87.5 degree Fahrenheit. The body is removed after 1 hour when they again took the temperature, which is 80.4 degree Fahrenheit. The normal temperature of a person when he is alive or she is alive is 98.6 degree Fahrenheit. So, you have to find an approximate time when the victim was murdered. So, let us start with the Newton's law of cooling, which says Tn plus 1 minus Tn is k times the difference between the surrounding and the temperature. So, if I put n equal to 0, I get T1 minus T0 is k times S minus T0. Similarly, you can get T1 is equal to T0 plus S into k minus k T0. So, 1 minus k times T0 into plus k times S. So, if I want n equal to 1, so T2 is equal to T1 plus k times S minus T1. So, this is 1 minus k times T1 plus k S. I substitute what is T1 from here and I get 1 minus k times T0 plus Ks plus Ks. So, 1 minus k whole square T0 plus 1 minus k into k S plus Ks. So, you can write this as 1 minus k whole square into T0 plus 1 plus 1 minus k into Ks. Just a way of writing. So, in the similar manner, if I go for T3, so this will be 1 minus k times cube into T0 plus 1 plus 1 minus k plus 1 minus k square into Ks and so on. So, if I want Tn, this will be 1 minus k to the power n into T0 plus 1 plus 1 minus k plus 1 minus k square plus 1 minus k to the power n minus 1 and whole multiplied by Ks. So, a simple GP series which is 1 minus k to the power n divided by 1 minus k, and this is 1 minus k whole to the power n T0. Here is k is here, this and this cancels, this becomes positive. So, it is 1 minus k whole to the power n divided by k into Ks. This also cancels and you are left with plus sign T0 minus S into 1 minus k whole to the power n plus S. So, some sort of formula. Now, let us calculate the time for murder. So, I rewrite Tn is equal to T0 minus S into 1 minus k whole to the power n plus S. So, after the murder, the forensic team arrives after, say, p minutes. So, the first equation is Tp. The initial temperature of the body is 98.6 and the surrounding temperature, let's take as 72. So, if I substitute this in this equation, so just at the point of murder, the temperature of the body is 98.6 minus the surrounding temperature 1 minus k to the power p plus 72. So, after p minutes, this temperature was found to be 87.5. I guess this information was already given here. The first one was 87.5 and the second one was 80.4. And after 1 hour, if I write it in minutes, this is P plus 60. The temperature of this T0 remains the same, the surrounding remains the same, 1 minus K, P is replaced by P plus 60 plus 72, but this temperature is 80.4. So, now you have to solve this. So, from the first equation, what we will get is 26.6 into 1 minus k to the power p is equal to 87.5 minus 72, which is 8.4. And from this equation, this is from 1, and from 2 you will get 26.6, 1 minus k to the power p plus 60 is equal to 80.4 minus 72. This is 8.4, sorry, this is 15.5. Okay, so now what you do is you just divide. So, I will divide 26.6 into 1 minus k to the power p plus 60 divided by 26.6, 1 minus k to the power p is equal to 8.4 by 15.5. It's approximately 0.542, and this cancels with this part. So, you are left with 1 minus k to the power 60 is equal to 0.542. So, you take log both sides and simplify, and you will get 1 minus k is equal to 0.9898, and this will give you k equal to 0.0101. So, you got the value of k and you substitute it here to solve for p. So, k is equal to 0.0101 and you get 1 minus 0.0101 whole to the power p, which is equal to 87.5 minus 72 divided by 26.6, and this value is 0.5827. So, you have 0.9898 to the power p is equal to 0.5827. This equation you get by substituting the value of k in equation 1, which is this particular equation, this equation 1. And you take log on both sides. So, you will get p equal to log of 0.5827 by log of 0.9898, and this value will approximately equal to 52 minutes. So, what is this 52 minutes? So, if you recall, after the murder, the forensic team arrive after p minutes. So, After 52 minutes of the murder, they arrived, and the time was 5 a.m. So, if you subtract 52 minutes from their time of arrival, what you get is an approximate time of murder. So, they arrived at 5 a.m. You subtract 52 minutes from there and you get 4:08 a.m. So, this gives you the approximate time of murder. So, this is how you use this Newton's law of cooling to solve the approximate time of murder. In case of this forensic team uses this particular law, which they do actually. So, summing up, in this lecture we see the application of Newton's law of cooling with two examples. The first one is about the temperature of a hot coffee which reaches the room temperature over time and supported by numerical results. The second one is much more interesting, where we use the law to find the approximate time of murder. In my next lecture, we will be talking about some discrete Dirac derivative model. Till then, bye bye.